previous one stopped recording at 11:44. Did you see it shut off? Whoever said that, who noticed that?
Listen.
Did you notice it shut off? Okay, cool. All right. Good catch. So what I was going to say is, if you've got an electron sitting down here in the ground state, the only way you can get this electron to pop up to say here, there's a gap here, and there's a certain amount of energy that you need an input for. Let's say it was this case. The energy gap here, the photon that comes in has to have exactly that energy. It's not like you can have a photon come in that has more energy than that, and it only takes some of the energy of the photon. It's like all or nothing. That energy gap has to exactly match the energy of the photon coming in. That's the only way you get these excited states. And then it like stays there a second, and then it drops back down. And then when it drops back down, that's when you get a photon coming out of exactly the same energy of a photon that originally came in. And sort of the point is, you've got this energy gap, you've got this energy gap, and you've got this energy gap, and maybe a few more. But photons coming in, like if you got photons of all different, like white light is generally all different frequencies, so therefore all different wavelengths, so therefore all different energies, and you're hitting it with white light, only the photons that have this amount of energy, or this amount of energy, or this amount of energy will be absorbed and excite one of the atoms in whatever sample is inside the sample. And every other one of the photons that come in and hit that atom, they bounce out. They have only photons of those particular frequencies will excite these, that is, be absorbed, excite the electron up. And therefore, those are the only frequencies that will come out. Once the electrons relax back down to here, it's only those three frequencies that will come out. So I don't think I said it both ways last time I told you all about this. But so if the laser light has that frequency and that amount of energy, that means that's the amount of energy in the gap when it drops down to send the photon back out. All right. What else? 26, I've got 27, 28, and 29. Calculate and compare. Hertz means per second. You know what? Take. So I'll take 28 off your list of things to study, and I'll do 29. The second sheet. We'll be doing these in lab today. So let me go on to my next sheet here to make sure I have time. If we have time, I'll come back. The next sheet is 7.25. what we're gonna do in lab. I can't get a printer working. All right, 7.25. We did a bunch of stuff in 7 and a little bit in 8. So 7.25. Okay, size of atoms. Do you remember this? 7.25, 7.26. I'll do 7.26. It's probably the ones I did last time. Wish I had my laser pointer. Barium, calcium, and nitrogen, and sodium. So I'm comparing for sizes. Barium, calcium. So this is 7.26A. These three atoms. As you go from left to right, no, we'll do it this way. As you go from top down on the periodic table, atoms are getting bigger and bigger and bigger. You're actually adding shells as you go bigger and bigger, so they get bigger. Non-intuitively though, going from left to right, things get a little smaller. So if you compared sodium and magnesium, magnesium is actually a little bit smaller than sodium. So now if we wanted to compare barium, calcium, and sodium. So barium's down low on the left, Ba. Calcium's a couple above there. And then sodium's even up above there. So sodium's going to be the smallest, calcium next, and barium the biggest. Smallest. And this was in the middle. You can do it like this, bigger than Ca, bigger than Na, Na being the smallest. I think the size trends are easy. So I don't think I need to go through all of those. Let's go on to 2829. Okay, the ions. I said skip A for 7.28. Definitely do that. Let's. So what if we did? 2, 3, 4, 5, 6. I'd say skip C for 2.28 as well. G, calcium. Size trends, BE. For those ions, the size trends are going to be the same as what I described before. What I really want to get to is, I almost want to say just skip up all of 7.28. Well, wait. Yeah, that's what I was trying to get to. 2.5 was that. Got 2.9. Yeah, skip 7.28. I won't put a question like that. The ions that I want to compare here. So we'll go to 7.29. 7.30. All right. Chlorine. So I want to go here. 7.30A. And I think that's best visualized with this game. S is right there. All right, if I'm going to put the electron configuration of chlorine here, 1, 2, 3, and all the way up to 1, 2. How many electrons total in chlorine?
17.
Yeah,
Neutral.
for the neutral atom, it would be 17. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That's the electronic configuration of chlorine. Chlorine. So if I didn't had question.
The neutral configuration has 17. The one it's showing has a
Yeah,
negative
I'm about to
charge.
get there.
Okay.
So this isn't what it's asking. But weeks ago, if I said, what is the charge on chlorine when it's an ion, what would you have said?
17.
Well, the charge on the ion
Oh.
is what that's showing. -1. You know what I'm talking about, right? If I said, what is the charge on sodium, you would look up there and count and you go, oh, it's +1. If I said oxygen, you would say -2. Chlorine is -1. It's -1 because it wants to fill out all of these. So it accepts an extra electron there, make it an extra color. And since electrons are negative, that's what makes it -1. So there's that configuration. What this is asking is, what is the neutral atom that is isoelectronic with Cl -1? So this has 17 protons in its nucleus and 18 electrons up here to make Cl -1. But there is a neutral atom that has this configuration. It has, right here, this is 18 electrons with 17 protons. There is an atom that has 18 protons. And the one that has 18, 1, 2, 3, 4, 5, 6, 7, 11, 12, 13, 14, 15, 16, 17, 18. Same as that one, I didn't draw them to the same level. So what atom is that?
Argon.
Yes. So it's like argon. If I went beyond there and went down here to potassium, that's argon. Potassium came plus argon, 19 protons. There's neutral potassium. But potassium comes potassium plus because it wants to lose that electron to get back to that octet. So that's what makes it positive. So what I would compare here, so the one that had 18 protons that has the same, that was argon. Argon is neutral. Chlorine minus, potassium plus. The point here is, you could look at that and go, they're isoelectronic, therefore the electrons in the outer shell are the same distance from nucleus for all of them, because they're all in the same level, the 3p, 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 all full. But the difference is this one has 19 protons, this one has 18, and this has 17. So the one with 19 protons is pulling it in tighter than the one with 18, and the one with 17 is pulling them in the least. So if you wanted to do a size trend, this is the smallest, argon next, and chlorine's the biggest, because those electrons are not getting pulled in as hard as these. So that's the effect. So this is just asking you which ones are the neutral atom that's isoelectronic. Iron, what do you do with iron? iron, let me do the electron configuration of iron. So how many electrons does iron have?
26.
Okay, 26. So if I were doing this, I'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So electron configuration of iron. I might just have you ignore the transition metals. What was I wanting to do? So iron 2 plus. Isoelectronic there is going to be,
Wait, did I miss you removing that orbital for a reason from 3D?
no, it's because I screwed up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 24, 25, 26. So is that right? That's what it would be. So isoelectronic here. Yeah. Ten. That one's okay. Yeah. For these types of questions, ignore the transition metals. That's these. These are the transition metals. So anything over here in that block, anywhere in the first two columns, I'll make fair game. All right, so where does that leave us? So questions like this, 7.31a, which ion is smaller? Fluorine negative or sodium positive? Fluorine -1. And it's the one with, since they're isoelectronic, they're isoelectronic with helium. Sodium's the smallest because it has the most protons pulling in on those electrons. Y'all get that?
Even though it's below?
Yeah. They're isoelectronic though, right? They have the same electrons in the same orbitals.
Oh, I understand.
The only difference between those three atoms, K plus, F negative, and neon, is the number of protons. And the one with the most protons is pulling those electrons in tighter. So this is what I mean, ignoring the transition metal. Okay, 31, 32, and chlorine and potassium I already mentioned. Same deal, potassium is going to be smaller than chlorine. I think that's it for those ion ones. 32, where does that take us? 33. Okay, consider S, Cl, and K and their most common ions. I think y'all can do those. 34. Ignore any of these that are transition metals. No, I'll just say skip 34. All right, what else in this chapter? Oh yeah, ionization energies. So the chart here, I wouldn't give you the chart, but I discussed this as so electron configuration of sodium. So the first one on this list, sodium ES. So that would be sodium. It's very easy for sodium to lose this energy. The ionization energy is how much energy it takes to remove an electron. I1 means we're removing the first electron, the most outer electron. I believe that's in kilojoules. It might be kilojoules per mole. Should have it somewhere. Do you see it? Well,
Up at the table description.
oh yeah, there it is. Kilojoules per mole. Okay, so yeah, kilojoules per mole. So it takes about 500 kilojoules per mole to remove this one. But then there's a huge jump in the amount of energy it takes. I2, or ionization 2, means removing one of these. So when you jump from one shell, we're in the number 3 shell here, or we're in the n=2 shell here. This one's very hard to remove because it's in this nice, neat octet that this likes. Okay, and then the next example, instead of sodium, magnesium. Looks like this. What does that say? 738 kilojoules per mole to remove the first one. Still a very low amount, 1451, to remove the second one. Realize it's a positive ion at this point, so getting this negative charge out of here is a little bit harder. So that's a little bit harder. So now we got a +2 charge for magnesium. And then it jumps way up. You've got a +2 charge, and on top of that, you're removing from this stable, neat octet here. So the energy jumps way up. So in general, ionization energies increase from left to right. Ionization energies decrease going from top to bottom because you're talking about, let's do magnesium compared to calcium. As 1, 2, 3, 4, 5. That's magnesium, and then if I want to go all the way to calcium, just below it. So first ionization energy is to pull this one out and pull this one out. The one below magnesium, calcium, that one's actually easier to remove than this one because the charge, magnesium 12, so a +12 charge in the nucleus. This electron feels that +12, but really these electrons and these electrons, they shield that negative charge from sensing the positive charges in the nucleus. And you would think calcium now with 20 would have an even stronger attraction. Really the difference here is there's more electrons in between this charge here. There's more negative charge shielding this positive charge from that electron. Ionization energies decrease going down the periodic table. So the general trend is ionization energies increase going from left to right and decrease going from top to bottom because of shielding. Once you get those big atoms, there's so many electrons in between the nucleus and the outer electron that it's just not feeling as much of an attraction to that positive charge. So that's the general trend. It isn't perfect, but you're seeing here, well, I won't say that. First ionization energy is shown here. So increasing from left to right, decreasing from top to bottom. There is a little bit of aberration here. But let's see what questions did I have? Was that 49? All right, let's go back to wherever. Yeah, so I gave you 49 and 50. So chlorine and argon. What? 49 and 50. Let's leave that one off. Ionization. And if I can give a smoother description of that, I'll put it on test score. So drop 49 and 50 on ionization energies. All right, and that gets us to 8. Chapter 8, 8.15. Okay, the Lewis symbol for these should be easy, but I'll just remind you. Lewis symbol, Lewis structure are synonyms. Lewis dot structure, it's called sometimes. So all you have to do, 15 and 60, yeah, 15 and 60, I'll do 60. Potassium. How many valence electrons for potassium? Okay. 1. The Lewis structure for potassium would be that. I really like doing the nonmetals better though. 10, Sn, right here. How many valence electrons for 10? Sn.
4?
It is 4. When you count valence electrons, you skip the transition metals. So you point at 10 and you go 1, 2, and then you skip 3, 4. 10 would be, yep, that's right. Everything in the column with 10, germanium, silicon, carbon, will all look like that. There's carbon, germanium, silicon, they all have 1, 2, 3, 4. Lewis symbol for those look like that. Since we're talking about nonmetals though, really it's the ones in the top right corner I'm concerned with. Because we're trying to deal with molecules here. But okay, Lewis structures, Lewis symbols. 15, 16. So now we jump up to 42. Is that all I had on those? Yeah, okay. 42 here, so electronegativity. I guess I'll bring that up. In 30 minutes, we might make it. So electronegativity is sort of the stepping stone to understanding bond polarity. So this chart is telling you, I probably won't give you this chart, but I'll give you these numbers as you need them. Actually, they're on those periodic tables I gave you for your test. The electronegativities are. So in general, electronegativities are lower on the left, and they go up as you go to the right, and then they go up as you go up. So fluorine is the most electronegative atom on the periodic table. Electronegativity means in a covalent bond, let's make a molecule here, fluorine. The two electrons that are in this covalent bond are being pulled strongly towards fluorine and weakly towards carbon. Electrons are negative, so so what we're comparing here is the 4.0 for fluorine and the 2.5 for carbon. The fluorine wins the tug of war and pulls those electrons towards itself. So this side is a little bit negative. This is a lowercase d Greek letter, and this is the negative. And then on this side of this bond is a little bit positive. I'm really talking about this bond here. Maybe I should do that. So the electrons are pulled this way, so we end up with what we call a dipole. You can also call it polarity, but there's some polarity to this bond. It's slightly negative on this side, slightly positive on this side. Carbon and hydrogen, those are neutral. Let me add, what should I put here? ONOH. So to decide whether or not there's polarity between two bonds, you use those numbers. So I probably won't give you this chart. Just remember the general trend. Left to right, electronegativity goes up. And then from bottom to up, electronegativity goes up. Let me look again at the problems I gave you here, because these should have questions about polarity. Two. All I want you to know here for 8.42, do I have 8.41 on that list? Let me look. Where is it? Well, 8.41 should be there. It's the one that it's similar to 8.42, but that's the one, 8.41 is the one that has the answers that you can look up. So those are very similar questions. That's fine. So that's just knowing that trend. Those two are about knowing that trend. 8.43 is next. Okay, this is where I want to go. Which of the following bonds are polar? So, and I'll come down here. So 8.43, 8.44. Let me answer 8.44. So 8.44a, I won't use that. So 8.44a. And it's having you compare a bond between carbon and fluorine, oxygen and fluorine, and boron and fluorine. The analytical way to do this, oh, should have brought one of my periodic tables. But does anybody have one of those periodic tables? This keeps me from flipping back and forth to that page. Let me borrow your table. So this does have electronegativities on it. Down in the bottom right corner. So it's just like that chart that I just had up of electronegativities, but it's got for fluorine 4.0. For carbon, electronegativity is 2.5. So that alone tells you that electrons are being pulled this way. Oxygen is 3.5. And boron is 2.0. All right. So I believe all of these are polar. 3.5 for oxygen, really? Yeah, okay. So what you do to get a relative measure of these different, how strongly polar they are, how big that dipole is, you go 2.5 minus 4.0, absolute value. This one's 3.5. The absolute value just helps you go, it doesn't matter which one you write correctly. It's sort of an absolute difference. I mean, it doesn't matter which one you write first, not correctly. I could do 4.0 minus 3.5. As long as I have the absolute value here, it doesn't matter which one I write first. This one is 2.0 minus 4.0. The difference here is 1.5. Difference here is 0.5. And the difference here is 2.0. So the scale is it's non-polar. It's between 0. I'll go ahead and write between 0 and 0.5. And we call that electronegativity difference. I'm using EN for electronegativity. These are electronegativity differences. These are the electronegativities that I got off the chart. So it's polar, non-polar. It's polar if it's 0.5 to 1.9. And it's considered an ionic bond if it's 1.9 or let's say but most of what we're talking about here is molecules, which are always going to be polar or non-polar, not ionic. If you're drawing a line between two atoms, you're talking about a covalent bond, so you're necessarily here or here, not an ionic bond. The complete word is polar covalent bond. But if we look at what we got here for electronegativity differences, 1.5 here is in here, so we would go, okay, that's polar, and if you want to indicate something, this side is negative and this side is positive, because that's got the higher number. 0.5, that one, I guess it's not polar, this one's non-polar. Or maybe you would say it's just barely polar. So if you're following this system, I guess that's polar, and this is, fluorine's the most electronegative one, so it's always going to be if fluorine is there, it's always going to be the negative side. If you have boron and fluorine, 2.0, you've reached into ionic bond territory. It is polar, but we would call this ionic. What is this asking? increasing polarity. So this is the most polar, I guess. This is so polar it's ionic. This is mid-range, and this one is just barely polar. I'm going to stick to these for the test, though, because ionic bonds are not what I wanted to talk about. Better question is 8.44b. So let's do 8.44b. So now we're being asked O to Cl, S to Br. C to B. Okay, good. These are all nonmetals. All right. So you look at the periodic table, and these numbers are on there. Carbon is 2.5 electronegativity. Phosphorus is 2.1. Bromine is 2.8. Sulfur is 2.5. And 3.0. All right. So comparing the polarities here, you're going to go 3.5 minus 3.0, 0.5 difference. Here we've got 2.5 minus 2.8, 0.3. This one is 2.5 minus 2.1. Those line straight up. So this is the least polar, and this is the most polar. When I say nonpolar here, there is some polarity. If it's not zero, there is some polarity. But we consider it nonpolar because it's so weakly polar, it just doesn't show up in any of the properties that we might infer from this. On test 4, we'll use this type of information to decide what will the properties, comparative properties, be like. Melting points and solubilities and things like that. So there's a little polarity, but from the standpoint of experimental stuff, what you can actually see in the lab, these between 0 and 0.5, it might as well be nonpolar, but it is technically polar. So this is the most weakly polar. This is the most strongly polar, but they are all very weakly polar to the point that it might as well not have polarity. Maybe this one, but that's borderline. So that's how you calculate these and how you compare them. Increasing polarity. Okay, that's simple enough. What else will I have to go over in the next 15 minutes? That was 4, 3, and 4, 4. 4, 9, and 50. Okay, these are drawing Lewis structures. So let's go through this real quick. I guess I'll do some of these. I probably did these last time. But I have to explain formal charge to do this well. Oh, I hate to do this. Thinking about dropping that. This today, test there, and then test 4 has to be here. So I really get 2 lectures but I'm really going to make that into 3 because one of our labs is written and it's all about stuff we're doing for test 4. So I'm really technically going to get 3 lectures in there. Yeah. Yeah. Okay, 49 and 50 skip for this test. And I'll change those practice sheets that I have on D2L, marking these off, the ones I keep eliminating. I guess we'll just do that. And that's it, that's all of them. I said to skip ionization energies, and I'm going to say skip drawing Lewis structures. I guess you can do the Lewis symbols of the atoms, but Lewis structures, I still have to explain formal charge. I don't want to do it at this point, so I'll squeeze that in for test 4. We really only have, for test 4, we really only have, there's a few things kind of scattered all over, but it's chapter 9 and 10. Yeah, it's tight. Chapter 9 and 10. But it's 9 and 10 and a couple other details. So I think we can do it. Do as much as I can. Our final is going to be the ACS standardized exam. But there's no way you're going to know everything that's on there. I have skipped some topics, so it'll be curved. All right, I guess that's good. We'll just stop there. Any questions? All right. Use the questions that I haven't crossed off these lists as practice for the test, because I don't think I'll have time to make a practice test at this point. Email me if you have questions. And let's see y'all in lab, but hopefully I can get a printer to print things.